AP Chemistry. We are going to overview Unit 5 in AP Chemistry on kinetics. This is a big one, so try to follow along and hopefully you can identify the areas where you struggle. So these are the overall concepts. First of all, is just what is a reaction rate? How can you represent that in a rate law? What are elementary reactions? What's involved in the collision model? What is a reaction mechanism? For multi-step reactions, what is a multi-step reaction energy profile show? And what is the effect of a catalyst on these things? So first of all, reaction rate. So in a reaction rate, you need to be able to explain the relationship between the rate of reaction and the experimental measurements. So you can measure different things to identify the concentration of a reactant or a product. And based on those things, it could be pH, it could be color, it could be precipitate, it could be the amount of mass, it could be a number of things that you use to measure the amount of a reactant or a product, volume of a gas, and the rate of reaction is determined by that experimental measurement. And I'm going to write down here, your rate is defined as the change in your concentration of something in a certain amount of time. Okay. So you need to be able to define the rate of reaction. You could be in terms of the reactants, or it could be terms of the products. If it's the reactants, the amount of reactants are going to decrease, and so your change is going to be negative, but you still would have a positive rate. If you're measuring your products, you would need to be able to look at the number of products over time. That is going to increase. Different chemicals, you would have to use stoichiometry to be able to represent the rate. So if you have a coefficient in front of a chemical, that coefficient tells you the ratios, and you would need to then use that factor in determining the actual rate of the reaction. So rates can be dependent on concentration. So the more concentrated the reactants are, the faster the rate is. Temperature, generally, temperature increases the rate of reaction. Every 10 degrees doubles the reaction rate. Surface area will increase the amount of reaction, the reaction rate, because there is more to react if it's a solid. And a catalyst can increase the rate of reaction. And so those are factors that depend on the reaction rate. So then we get to the rate law. A rate law is a expression that represents a data in a reaction. Some reactants react differently with things. So your rate in a rate law is your K times the concentration of a reactant raised to some power. Okay, and then you could have another reactant, maybe. It's always based on the reactants raised to that power. So the concentration raised to those different powers. So that is a rate law. Rate laws are determined through experiment, and often you'll be given a table of the rate and the amount of A, the concentration of A, the concentration B, and the rate. And you'll have a table of that, and then you have to use logic to figure out what power A is to and what power M is to on the B. The rates are proportional to concentration raised to a power. So that's what this is. It's some power, and that is the order of the reaction. So those N's and those M's are representing order. You can have first order, second order, third order reactions. You can even have half order reactions that you can do. So we talk about order of reactions. And then you would need to be able to determine the rate constant, which is your K, and be able to get the units of the rate constant by using math and unit analysis. So that's the rate law. the concentrations over time. This is a big one, it involves a lot of calculation and graphing. So you should be able to show how the concentration of reactions and products change over time. Generally, what's going to happen is if you have the concentration of a product over time, generally it's going to decrease over time, doing something like that. Okay, because the reactants get used up and the products get formed. So the products then are going to increase over time, right? So you should be able to show the changes of a reaction in terms of reactants and products over time. So the graph will depend on the order of the reaction. Is it a flat graph? Is it a curvy graph? Is it a really curvy graph? Depends on whether it's first order, second order, zeroth order reaction. So first order are proportional to the natural log of the concentration. Second order are proportional to the inverse of the concentration. And I'm going to show you that down here in just a second. And then you have the equations that you need to use for first order and second order reactions versus time. So I'm going to look down here now. So first order reaction, these are your general equations. They're in two forms right now. You can have the natural log form, and time 0 is the concentration at time 0, and T is the concentration at some other time. And that would be the equation that you would use, and it's proportional to natural log for first order. If you were to look at the graph of that down here, this is what the curve looks like. It's just the reaction, the concentration of A decreases in time in this kind of inverse sort of way. When you plot the natural log, you get a straight line. When you plot the inverse, you do not get a straight line. So this is saying that the natural log is it's proportional to the natural log. For second order reaction, it's not natural log, it's the inverse relationship here. So 1 over minus 1 over equals kT. And that's a second order reaction. It's a very similar curve for the concentration, but when you do the natural log, it's not a straight line, but when you do the inverse, it is a straight line, and so this shows an inverse in second order. For first order reactions, you can also use the half-life calculations, and down here is the formula for the half-life calculations. So the half-life time is 0.693 times K, which is the rate constant, and that is going to give you your half-life, and you can use that. So remember the half-life, every time you reach this amount of time, half-life time, your concentration will be halved. If you reach it, so if I'm looking at this graph down here, let's say I start up here at 20, and when I get down to 10, it looks like it takes about 7 seconds to get down to 10. So I 6 or 7 seconds, I'm halving it. In another 6 or 7 seconds, let's say I'm up at 12, it halves again. So it goes from 0.2 to 0.1, and then it halves again to 0.05, and then another 6 or 7 seconds is going to go to 0.25 or 0.025. And at every half-life, it will half. So that's the concept with that. Radioactive decay is actually like with nuclear stuff, follows first order, so half-life follows the first order kinetics for that. So those are the concentrations over time. Elementary reactions. All right, so we have these list of elementary reactions, and this is a reaction where two molecules hit each other to form a reaction. Okay, so there are different sorts of elementary reactions. You can have first order, second order, third order elementary reactions, but it's determined by the coefficients in there. If you have just A breaks up into, let's say, B and C, this is just an elementary first order reaction, and so your order is 1. If it is, and your rate law would be the concentration of K just to the A. If there's 2 in front of the A, then that is going to be a second order reaction, and you would raise it to the power of 2. And then you could have 3 in front of that as well. Or you could have 2 different reactants, and they both add to give you a order of 2. Okay. 3 or more are very unlikely to have simultaneous collisions and are very rare. If you do have a reaction that does do that, then it is going to be a very slow reaction. Okay, so those are elementary reactions. Only elementary reactions can you get the rate law from the balanced chemical equation. So then there's a collision model. This is also called Arrhenius' equation. There's 3 factors here. You got the frequency of collisions, how often the collisions happen. You have the energy needed to cause a reaction, and then you have the correct orientation. I put generally what factors those depend on. So the higher your temperature, the more frequent your collisions are, but the higher the temperature, also the more energy the molecules will have to do that. Your activation energy is determined by the type of reaction, and orientation is do molecules have to be in a certain rotation in order to actually react. So generally, only a very small fraction of collisions lead to a successful, and that is usually given by that A factor. That A is the success rate of the collision. So Arrhenius' equation relates to that. This is Arrhenius' equation down here in 2 different forms. One's a natural log form and one's an exponential form. You have your activation energy, you have your temperature, and you have your collision factor. Your R is the gas law, but you do have to use the joule version of it, the 8.3 something version of that to be able to do that. And that's going to give you your rate constant, and the higher the rate constant, the faster the reaction is. Maxwell-Boltzmann's distribution of particles, this is this other graph over here, shows you a picture of what reactions will actually produce a reaction, or what collisions will produce a reaction. So let's say that 600 here is about where our activation energy is. Anything that has a lower energy than that is not going to react. So all of these are not going to react. Anything with a higher energy than that will react. Check. So if your temperature is, let's say, 300 Kelvin in this picture, many of these particles are not going to react. Okay? So this is representing how many particles will react in there. If, however, you raise the temperature, then you got all of these particles are going to react. And so you'll end up getting a lot more of the collisions will result in a reaction. So Maxwell-Boltzmann's distribution helps to identify that. You also see Maxwell-Boltzmann's distribution when we talk about gases. All right, energy profiles. So the reaction energy profile is where you start with your reactants and you end with your products, but they have to go up through this activation energy. So you should be able to represent the activation energy and the pathway for an elementary reaction. So when you only have one hop here, this happens to be an endothermic reaction. Your activation energy is the amount of energy needed to get to this first transition state, and then it will do that. The over on the reactant side, going up the hill, this is where you're breaking bonds, and going down the hill, you're forming bonds. And in general, that's going to be the process right here. And you get to a transition state up here at the top, where you would have some intermediates, maybe, that will then react to form the products. Your reaction rate is dependent on the activation energy. So if I'm going in the forward direction, I have a very large activation energy. This is saying that this reaction is going to be pretty slow. If, on the other hand, we go in the reverse direction and we go this way, the activation energy is going to be smaller because of this, and it would be faster going in the reverse direction than in the forward direction. Identify transition states and activation energy and the total enthalpy. This is the total enthalpy over here. It's endothermic in this reaction. Show what determines the rate of the reaction. It's your EA, and discuss how temperature plays. So again, if you have higher temperature, you're going to have more of these molecules, these reactants that have enough energy to get over the activation energy. All right, reaction mechanisms. So the mechanism is here's an example of a reaction mechanism. It is the different elementary reactions that in steps that will lead to the overall reaction. So you need to identify that a reaction mechanism is a series of elementary reactions. In this case, we have step 1, you take 2 NOs and it reacts. In step 2, you take an N2O2 and it reacts with an H2, and in step 3, it takes an N2O and reacts with an H2. Okay, so those are 3 different reactions that all happen for the overall reaction. So you need to identify the reactants. In this case, we have 2 NOs as our reactant. That produces an N2O2, but then that N2O2 becomes a reactant, which is not technically a reactant, but we do need another H2, which then produces the N2O, and then another H2 is going to react. So we need 2 NOs and 2 H2s are our reactants. Okay. Then you should be able to understand intermediates. Let's do intermediates in red. Okay, so our reactants are blue, our intermediates are red. Intermediate is what forms in the middle, but then is there. So we have an intermediate with N2O2, and it is then used up. We have another intermediate of N2O, and it gets used up. So it's actually not part of the overall chemical equation. And then we need to be able to identify the products, what gets produced. Well, N2O2 is not an overall product, but our H2O is a product here. And then we have another product, another H2O, and another N2. So we have 3 of those. And then a catalyst. In this case, there is no catalyst, but a catalyst would be something that you use as a reactant. It forms something, and then it reforms into a product, and it's not part of the overall balanced chemical equation. So then you should be able to get the overall balanced chemical equation. In this case, it's 2NO plus 2H2, arrow 2H2O plus N2. And that would be your overall. Describe and identify what an intermediate is. So we talked about that. And then an experimental detection of an intermediate helps to support the particular mechanism. Okay, so these are reaction mechanisms. And then how does reaction mechanism relate to the rate law? Well, the rate determining step is your slow step. So what is your slow step? You need to be able to do this for 2 months. If the slow step is the first step, check. If it's not the first step, okay. For the first step, then your rate law is just determined by that elementary reaction. If it's not the first step, then it's determined by that step and any intermediates that are used. And so you have to do that. So if I were to go back to this one, here our slow step is our second step. So the rate law is determined by the N2O2 and the H2. So you would use those. But I will write this down here. So your rate is determined by those 2. It's going to have a K value. And then you have H2, but H2 is a reactant. That's fine, but N2O2 is not. N2O2 is produced by having 2 NOs. And so you have to use that intermediate to go all the way back to the original products, and you need 2 of those. And you need the H2 as part of that. The other H2 that happens in the third step is not part of the rate law because it's determined by the slow step. Okay. Multi-step reaction energy profile. Here, same idea, except for you have many activation energies and stuff. So you need to be able to identify different things in these. The Different activation energies will actually speed up the reaction because you have less energy that you need to overcome. Instead of going from the beginning reactants to the very tip, you go into these transition states. So you have your intermediates are going to occur at the bottom of these. You'll have two different intermediates that then get used up as part of the reactants. Your transition states are at the peaks of these. So you should identify those. And then your reactants are the beginning and the very end are where your reactants are. But each one of these represents an elementary reaction step. Right? And then if you have a catalyst, explain the relationship between the effect of a catalyst on a reaction, the changes in the reaction mechanism. So a catalyst speeds up the reaction by lowering the activation energy. So it lowers the EA. Here is an example of a reaction mechanism. If it was an overall reaction that was very slow, the black one, a catalyst will produce some intermediates and it will make it a faster reaction because all of these EAs are much smaller. So with a catalyst, the EA is smaller than without. There's different types of catalysts. You might want to look those up. But one of those is where the catalyst is used as a reactant and then returned as a product. And so it's not part of the overall equation. Some catalysts bind to a reactant, so they become part. The reactant binds with the catalyst, and it actually provides a better orientation to do some more. So enzymes are an example of a catalyst. And that is a summary of kinetics.